All right, welcome back. So again, we're looking at the idea of how to find the absolute maximums and minimums of a function. And we said, well, if you're going to have a maximum or minimum function value, there's only two places where they can occur. They are at the endpoints or at a critical number where the graph is changing direction. So that's what we have to look for to find absolute max and mins. Now remember, these are not relatives, these are absolute, the exact tallest point on there. And what we do is we just compare their values. Right there. All right, so let's take a look at another example for like number 3 right here. Now be careful, they do give us a domain restriction. They do give us a domain here. Because we can't have a value at -3, but we're not really too worried about that one. So again, the first thing we're going to do is find the critical number. And when we find the derivative, remember the best way to do this, the best way to find the critical number, the derivative here, is quotient rule. Don't try to be fancy using product rule, you're just going to hurt yourself. So we would get low at the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So there's our critical numbers right here. I mean, sorry, not a critical, our derivative. If I clean this up a little bit, we're going to get 2x squared minus x squared, or just x squared, plus, if you do this right, you will have 6x over x plus 3 squared. So, to get our critical numbers, 1, set the derivative equal to 0, or where does the derivative not exist? So, if we solve it, the top, remember for this one, for where the derivative is 0, remember we're only looking at the top here. So, if I factor the top, I'm going to go and do that right away, I'm just going to factor it. We're going to get x equals 0, x equals -6. So 0 is 1, but -6, this is out of my domain. So I'm not going to worry about that one. This is out of the domain. So I don't have to worry about that. Where does the derivative not exist? This is where we look at the bottom of the function. Thank you, Leibniz. So that's going to be this x plus 3 squared equal to 0, where the bottom is 0. And we just get x equals -3. But like the first one, like this -6, this is out. Whoops. Let me do that in red. This is, again, out of the domain. So I really don't have to worry about that. All right, after you find the critical numbers, the next thing we look for are the endpoints. And remember, they have to give us those. They are x equals -1 and x equals 3. Notice, I start at the extreme left and I go to the extreme right. I work my way to the right. Candidates test. The candidates test, you don't have to write out the word candidates test. You can show it too. Just make sure you show it somehow. So we have our x's and we have our function, which remember is going to be x squared over x plus 3. Our endpoints, I use my endpoints again as bookends, -1 and 3. Those are my endpoints. And I put my one critical number, 0, in the middle. And this one I could probably do in my head. If I plug -1 in, I'm going to get 1 over -1 plus 3, or 1/2. 0, that's just 0. 3, I'm going to get 9 over 3 plus 3, which is 9 over 6, which is 3/2. So our absolute maximum, let's go ahead and find this, as a point is going to be 3/3. Our absolute minimum value, the smallest value on this domain, remember, it's not necessarily the smallest value on the graph, but it's the smallest in our domain. We use restricted. If I say, who's the greatest calculus teacher on this video, you should say me. Everything is good when you restrict the domain. An absolute minimum would be at 0, 0. And those would be our answers right there. So let's take a look at a couple special cases. All right. For these two, we're going to sketch. Man, I promise you, sometimes you do not want to take the derivative of absolute value. It is not pretty. So we're going to sketch it. We're going to do everything the same, but we're going to sketch these. So for the first one, when we're looking at this, when we're looking at our critical numbers, to sketch this, let me sketch this first. To sketch this one, you might remember we don't like the 3 here, so we're going to factor it out. And this becomes x minus 4/3. There's our graph. Now, you might remember in pre-cal that this gives you the x coordinate of the vertex. So graphing this at a horizontal shift of 4/3, this is going to be absolute value. And that's what absolute value looks like. Next, I find my critical numbers. I'm still going to do all of my work I did up here because I want to show the AP I understand this. 1, where does the derivative equal 0? Nowhere. There's no 0. Remember, this is a corner right here. This is a corner. The derivative does not equal 0. It's a corner. But is there a place where the derivative does not exist? And that's yes. X equals 4/3. Do we have any endpoints? Yeah, they give us 0 and 3. I should give myself a little more room. All right, so let's go ahead and do our candidates test. Set it all the same way, x, f of x. My endpoints, 0, 3, and my one critical number, 4/3. If I plug 0 in, I'm going to use the original, the OG. If I plug 0 in, we're going to get 0 minus 4, which absolute value is positive. If you plug 4/3 in, well, that's obvious. That should become 0. We can see that on our graph, right? And if you plug 3 in, this becomes 9 minus 4, which is 5. So where's my absolute max? It's going to be at 3, 5. And my absolute minimum is going to be at 4/3, 0. Remember, we're looking at those y values. I'm comparing them. Very easy. Now notice, even though I graphed it, I still showed my steps. I want to show candidates test, or the extreme value theorem, so I have to show my critical numbers, show my endpoints, show I'm comparing the values, and then I write my answer. And that's it. It doesn't take long. What did it take us? What, 2 minutes? All right, number 4. Okay. Again, don't just the 4. Let's make the 4 a hard bracket. I'm sorry about that. We'll make that a hard bracket right there. Okay. So when you're looking at a question like number 4, this is our rational function. We know what rational functions look like. This has a vertical asymptote at 3. And I even know which way this is open. If I pick a point, right? If I pick a point, let's say 0, I know it starts underneath here. So it looks kind of like this. Now, if I'm looking for so there's my graph, so now I'm going to get my critical numbers. Is there any place where the derivative is 0? The answer is no. It never becomes 0, even if we go on forever. It approaches 0. It's a limit problem there. Uh-oh. Is there any place where the derivative does not exist? Notice I'm still showing these. And yes, there is actually a place. X equals 3. But it's a soft 3 on the domain, so this is, again, out of the domain. So this is out of the domain, so I don't have to worry about it. Next, any endpoints? Yes, they tell me 3x equals, they do tell me 3 and they do tell me 4. However, the 3 again is out of my domain, so I don't have to worry about it. So how many points do I have to check? Only 1, 4. So when I do my candidates test, it should be pretty easy. There's x, there's f of x. I just plug in 4. So there's 4, and if I plug it in, be very careful. If we plug in 4, we're going to get 1 over 4 minus 3, which is 1. So let's take here, where is my absolute max, and where is my absolute minimum? This is why the graph becomes important. If you look at the maximum, notice we're approaching the asymptote. We never reach it, so there isn't any. So there's no absolute maximum. The absolute minimum on our domain that we want, this is the only part of the domain we want, we really don't care anything here, it's going to be at the 0.41. So here we used the candidates test and our graph to kind of get the answer there. We had to use both of them there. One thing I'll be looking for when I'm grading, is how, even on the AP, showing all your work, especially when using the candidates test. All right, so I hope you guys enjoy these videos, and smash that like button. I'll see you guys later. Bye-bye.